Hello, welcome to Breadboarding. My name's Dave Henry and this is the second video in the Breadboard PC series where I'll be showing you how you can build a PC capable of booting MS-DOS on breadboards from the ground up. In the first video in the series, we came up with a high-level plan. So this was to develop a PCXT hybrid computer based on the Intel 8088, which was the processor in the very first two IBM PCs. And we were going to, first of all, build out something similar to the Nanocomp computer that I have recently completed on the 6809 microprocessor. Then we're going to build that out to be able to use basic floppy disks and to be able to boot an early version of MS-DOS. And then we'll look at extending that to add a disk controller and a color graphics card and be able to run up Windows 1.0, 2.0, very early versions of Windows. So background info for this, there's an awful lot of information available on the PC, obviously, and these are some of the sources I've used. So I'm going to go through these in summary. And the first one I was just going to take you through was Personal Computer World magazine from November 1981. This was just a month after the IBM PC was released in the USA. So this is Personal Computer World magazine from November 1981, and this is one of the main magazines that was in the UK, published in the UK at the time, and this is one from way back then, 42 years ago. And there's a 4 or 5 page review of the IBM PC in here. I will scan it and put it up on the GitHub site for the project for those who want to have a little look at it. The interesting thing about it really was the prices in the back. 64K add-on memory board was about $540. So if you think that a 512K chip now costs less than $10, so it's about $8,000 worth of RAM there. And the specified sort of with a printer and a monochrome display and floppy disk drives would be about $4,500. So it certainly wasn't cheap, but obviously was groundbreaking. So in the other source I've come across, there is a book from about 1989 by Robert Grossblatt. Now, I'm not actually using this directly, but it is interesting from the point of view of some of the background on this. So the 8088 project book is available on archive.org. And what this basically covers is a lot of the background to the 8088 processor and some of the supporting chips. And it basically builds out a clock, a digital clock on breadboards during the whole book. So it's definitely worthwhile having a look at that. And in particular, there are quite a lot of laws and rules that Robert includes in here, and I have actually assembled a number of my favourites, and I'll cover those in a second. So the laws of life and design, which are in the URL above. Golden rule, think for yourself. So I think in all of these sorts of things, if you just blindly follow instructions and information that other people give you, sometimes there are mistakes out there, and certainly I'd warn anybody working from my material, I'm not immune from making mistakes, so please think for yourself. Another interesting one is done on dynamic RAM. Using dynamic RAM in a single board system like ours, in words of 2 syllables, a mistake. And a number of the other key ones. Knowing what you want to do before you try to do it is a very key one, and that's what I'm going to be laying out here. There's no substitute for a data sheet, absolutely. Sometimes you do have to study the data sheets in quite a bit of detail, and it can save you a lot of time. If you can't afford to blow it up, then you can't afford to use it. And most of the chips here I've been able to buy on eBay. Some were getting to about £15, £20, $25 a chip, and certainly I would be upset if I was blowing up 1 or 2 of those. But in general, most of what I'm using here is in the £5 to £10 range. Some of these other ones here I've just included. Anything which can blow up will blow up. I've developed quite a knack for blowing up tantalum capacitors. You put one of those in the wrong way around and it goes crack and smoke pours from it. And the other key one, a circuit of 1,000 parts starts with an LED, which I like in particular. So it's worthwhile having a look at that book. Quite a light-hearted view on the world, but there's an awful lot of good advice in there. But probably the most key resources for this is the reason for the IBM PC success, I believe, was the documentation that was provided with it. And in particular, the technical reference manuals were superb. And in fact, they even include the full design and the BIOS listings for the early versions. So this is one of the logic diagrams from the PCXT. And we can see here that this is the processor itself. This is the clock circuit. the bus controller, and these are some of the buffers. And this is really one of the circuits that we're going to be basing a lot of the early project steps on to get the basic processor working with the necessary clock and bus control circuits. But I should say that the technical reference here was extremely comprehensive and includes virtually everything you could want to know about these computers. As I said, it also includes a BIOS listing. I'll put these up on the GitHub site as well. And then the PCXT, similarly, broad similarities here, but there are a few things like keyboard controllers and the timer, for example, that was introduced into the 80. And I will, when we get to later stages in the project, look at the Compaq Desk Pro 386 technical reference guide as well, because these include the circuit diagrams as well. So I'll include the links for the various XT80 and PS2 technical references. PS2 becomes interesting when we start to look at the PS2 mouse and PS2 keyboard controller. And there is another excellent site. So Sergey Kiselev has a GitHub site which includes the XI8088. And this is a PCB based 8088 PC. And what he's done in the diagrams, circuit diagrams, and for this has largely updated the 8088 XT design to cover things like the 8042 keyboard controller, the real-time clock chips and things like that. So I'm going to be trying to build something similar to what Sergey's developed here on breadboards. This one was designed to plug into a ISA backplane and then to be able to just plug in standard IBM PC cards. What I'm taking the approach is that while I will have some form of backplane that I showed on the Vero board in the last video, I want to really try and build as much of this all on breadboard. So I'm not going to be using any plug-in PC cards. I'm just going to be building everything from the ground up. And hopefully that will allow to understand exactly how this sort of stuff works. But the other key thing here that we will need before we can actually run MS-DOS is that Sergey's got a version of the BIOS, the basic input-output system. So this is the software that really starts up the PC and what does things like the memory checking and initializes all of the chips before it even attempts to start to try and load an operating system. So until we can get a compatible BIOS running, then we don't really have any chance in running MS-DOS. And I'll just show you the circuit diagram. So it's a very comprehensive circuit diagram, nicely laid out. And we'll be coming back to this when we're looking at the clock and reset logic, and particularly some of the bus arbitration and wait logic is quite complex in the original designs. And because we have static RAM and not dynamic RAM, then this can be simplified somewhat. So I'll be calling on some of Sergey's skills here on what he's already worked out to try and do this area of the circuit. We'll also be referencing back to the original Wireless World Nanocomp schematic, which I showed in the earlier video, and this is primarily to get the LED display and keypad running. And the reason why we want that LED display and keypad is that the Nanocomp monitor that I'm currently redeveloping from assembly language into C, when that is able to run, then it will allow me to get the monitor and this LED display and keypad running on the 8088. So it'll give me a very simple operating system to be able to work from as we start developing the MDA video card and later graphics card. I'm thinking that this is almost going to be like the built-in BASIC that used to be in the original PCs. If there wasn't any floppy disks, it would just start up in BASIC. What I'm thinking of doing is using this Nanocomp monitor effectively as the basic ROM, that if nothing else loads, at least it goes into the monitor, and then we would be able to load programs over the serial port and set breakpoints and do various things like that. And I will be summarizing all the information from these distant sources into a project KiCad schematic. And again, I will put all of these up on GitHub once we get to an appropriate stage. Okay, so I'm just going to cover some of the simplifications I've made decisions on, and this is also partly what Sergey has done in his XI8088. So I'm going to be trying to use early 1980s components where possible, but there are some exceptions for practicality, cost and or availability. And some of these things you can still get, and I know there are sites out there where people are restoring legacy PCs and with original keyboards and everything else, but really what I'm trying to do here is learn how to make a PC work from the ground up, not really trying to build a 1981 authentic one, although I would like to try and keep to the 80s components where possible. Occasionally I have to stray into the early 90s because certain things like floppy disk controllers and things were much simpler when they were bundled into one chip. So we're going to be using static RAM over legacy dynamic RAM. It reduces the chip count for buffers because we've got a much smaller number of chips we need. There's no refresh requirement and no wait states. So as the project book shows, it's a mistake to try and use dynamic RAM on a modern project. I'm going to be using modern electrically erasable programmable read-only memory rather than legacy EPROM. This simplifies the programming, they're faster generally, and we don't need to use ultraviolet lamps to erase them. I'll also be using programmable logic devices, PLDs, to simplify some of the logic and decoding. These were starting to get introduced in mid-1980s design. Certainly the Compaq Despro 386 included a number of PLDs in the design, although these were not in the very first PCXT. I'll be using a 3.5-inch floppy disk drive and PS2 keyboard and mouse, and these were introduced in the PS2 range around 1987, and again that's more down to availability. In the Nanocomp series, the 6809 series, I showed the working with a 2.5-inch laptop SATA hard disk with an appropriate SATA to IDE converter, so I'll be using this rather than trying to work with a legacy IDE drive. And on the video side of things, the monochrome display adapter that was probably the simplest display adapter with the PC, that had a dedicated monitor and ran at a resolution of 720 pixels across by 350 lines and 50 hertz. Now, modern monitors, LCD monitors, can't really work at that, to my knowledge anyway, and so what I'm planning to do is to work the video output of these at VGA resolutions, and that may involve using 640 by 400 at 70 hertz, for example, which would give us something like 8 pixel wide characters rather than the 9 pixel wide characters that the monochrome adapter did. So those are the simplifications we're going to use. So I'm not building exactly as it was in 1981 or 1983 when the XT came out, but it will be close enough to be able to run all of the software from that era. So I'm going to be using the monochrome display adapter MDA, and why not do the CGA, EGA or even VGA? Well, we need PC compatibility for standard DOS software to work. Now, the Nanocomp video controller I built in the previous series produced VGA compatible output, but it was not PC register compatible, and the way how the memory map was done, things like that, was not the same as on the PC platform. Now, the monochrome display adapter is simpler to develop, and especially using dual port video RAM, and this means that we won't have display flicker and things like that. The EGA and VGA graphics cards actually had introduced custom very large scale integration chips for control registers and things, so these were like 144 pin, 160 pin surface mount chips. So really, even using EGA and VGA chips would be quite tricky for breadboards to use these sort of highly integrated circuits. And the other advantage of the MDA adapter is that it can coexist with other video cards, so you can actually use it for debugging. So as we start to develop the CGA, MCGA adapter, then in fact we can still continue to have the MDA board plugged in and running at the same time. So I do plan to develop a CGA color compatible adapter later, and that will again hopefully be register compatible with PC, so it should be capable of running most PC software. And I may very well extend that into the MCGA, which I talked about in a previous video, which is a little known standard that added a couple of the higher resolution color and 640 by 480 two-color graphics that then arrived in VGA. So it kind of sort of bridged the CGA and the VGA world, and were certainly two resolutions that the Nanocomp 6809 video controller supported. The MDA has hard-coded ROM-based fonts, so that makes things a bit easier. The original card included a parallel port, but we don't need that for running printers. What I am going to do, though, is to use the VGA video digital analog converter palette chip. Although that wasn't obviously in the monochrome display adapter, I think it will be easier to produce the video signals. And in fact, a little known fact that the monochrome display adapter could in fact do 16 colours with some versions, and if plugged into a suitable monitor. So it may very well be we can get the MDA adapter even to do colours as well. So the MDA adapter is going to be 80 columns by 25 rows, so that's 1 byte for the character, 1 byte for attributes, so that gives us 4,000 bytes. And the reason why we're doing 25 rows rather than the 30 we did in the previous card is because we're limited to this 4,000 bytes. The dual port video RAM is just in 4K chunks. As I said previously, The MDA used to have quite nice wide characters, but we're going to squash this down to from 9 pixels down to 8 and make them more like the VGA ones. And that will allow us, rather than having this horizontal refresh frequency at 50 Hertz, it'll allow the VGA output to be compatible with the monitors and the video capture cards that I've got. So I'm just going to take you through the high level diagram for the first couple of stages of this. So we're effectively building a Nanocomp 8088 until we can get to a stage where we can boot things up into the Intel world, and then we can start to build out video controllers and try and get the floppy disk controller and things like that working, so we can then start to boot up DOS. So what I've done here is a similar diagram to what I used in the 6809 series. What I've done is I've changed some of the colors for where things are different from the previous series. So we've got a faster clock here. So this rather strange clock frequency, 14.3 megahertz, that was actually a multiple of 4 of the US NSTC TV signal. So the idea of using a multiple of the TV signal meant that the graphics cards would be able to output appropriate NSTC compatible color signals. It does have a dedicated reset and clock circuit. So the key thing really about the 8088, because it was trying to do 16-bit processor in a 40-pin chip, there were some compromises in the way how some of this stuff worked, and so there's an external reset and clock circuit, unlike the 6809, which had a lot of that built in certainly some of the chips. So the 8088, although it's a 16-bit processor internally, only has 8-bit data bus, so that makes it a lot easier for doing in breadboards, but it does slow things down a little. And the address bus now, unlike the Motorola 6809, which was just a 16-bit bus, this has got a 20-bit bus that gives us a mighty 1 megabyte address range. And obviously the famous phrase that Bill Gates is rumoured to have said and denies ever since, that 640k should be enough for anybody. At the time when everyone was working with 64k address space, 1 megabyte was absolutely huge. And then there'll be control signals, so things like the reset signals, the memory read and write, the IO read and write, and interrupt signals as well. Now the key thing with the PC and PCXT used the Intel 88 in the maximum mode. It had 2 modes, minimum and maximum. With a minimum, you probably could put a simple circuit together without needing some of this external circuitry here. But because the PC used the maximum mode, then I'm going to go straight to the maximum mode first of all with the bus controller, and then with the buffers and latches, and this handles the situation of how you get your 8 data bus and your 20 address bus out of the limited number of pins. So these buffers and latches will basically then give us effectively a running microprocessor for which we could then do something useful with. Then we're going to add an address decoder similar to what we had before, but this time obviously we've got quite a few more address lines to decode. We'll add some ROM. And at this stage, that's where we're going to start to try and add the Nanocomp C monitor. So that should hopefully allow us to start to do something useful. At the same time, we'll be adding some RAM. I'll probably add about a 512k chip, so half a megabyte chip in one chip here. Then we'll add the peripheral interface adapter. Now I'm probably going to use the same one that I used on the Nanocomp, just from the point of view of all of the initialization for all the registers and things are the same, and so for the moment at the early stages we'll just use some of the Motorola chips. And in fact IBM used Motorola 6845 video controllers anyway in the MDA and CGA cards, so it's not as if there aren't going to be the control signals needed for this. So then once we've got this, we'll then be able to add the 7-segment display. Now the only difference here is the original design and the keypad, I should also say. The only difference here is that it was using a 1 to 10 decoder, and unfortunately we actually need to use more than the 6 segments that were used up here on the original Nanocomp. I'm going to allow to use for all 8, and that means we don't have quite enough lines to do the keypad and here. So I've added an extra decoder in here that will split out the scanning of the keypad from the driving of the LED display. So all this does is splits the signal out into a range to allow us to actually use all 8 segments of the LED display. So that's as much as I wanted to do in this video. Referring to the high level plan, in the next video what I'll be doing is looking at getting the clock and reset circuit running. So I'll be covering that in the next video, hopefully in the next week or so. So thanks for watching. If you don't want to miss out on future videos and you're not subscribed already, please hit subscribe, and if you hit like, it just helps these videos to reach a wider number of people. Thanks for watching.